Hello once again, ladies and gentlemen, and welcome back. We're on the very last question, question B3 of the 2016 Canadian Senior Math Contest. It's a hard question, but I would encourage you to try and pause the video and try this question out for yourself, even if you only make it through, parts A or B, just to give them a try and really see how much you can do before you come back and see how much I can do. Hopefully that's all of it. But what have we got with question 3? Well, it's a written question, as the last two have been. And we've got three parts to it, A, B, and C. What have we got here? For each positive integer n, define an and bn to be the positive integers such that root 3 plus root 2 to the power of 2n is equal to an plus bn. So it's interesting that we can get positive integers out of this. Not necessarily what I would expect, and also if root 3 minus root 2 to the 2n is an minus bn root 6. Okay, so I've seen things like this before. Most commonly I've seen it when I was solving things like Pell's equations. So trying to solve something like x squared minus 2y squared equals 1, you'll get solutions, and this guy can be factored into x plus root 2y times x minus root 2y, and then if you got a solution like 3 and 2, to get another solution you would square them or cube them and that sort of thing. So that's Pell's equations, and that's what this most reminds me of, this particular setup, because you'll take a solution, x naught, y naught, and you'll get a brand new solution by cubing these or fourth powering these. And that's definitely what I'm reminded of. The square root symbol, the raising it to some arbitrary power to get other numbers. This is definitely, to me, reminiscent of Pell's equations. Okay. I don't know if any of the knowledge that I know about Pell's equation and all these techniques will help me, but let's read on. So determine the values of A2 and B2. Okay. B part, prove that 2 times an minus 1 is... Okay, so we got an interesting little range here. And C, let dn be the ones digit of the number when it is written in decimal form. Yikes, okay. But I'm guessing B part will help me figure out what that ones digit should be. So we get the ones digit. Determine with justification the value of the sum of all the ones digits. Okay. For 1867. I wonder why they chose 1867. It doesn't have any particular math properties. I mean, it's when Canada became a country, but nothing is particularly coming to mind in terms of being helpful. Okay. All right, well, let's just jump in with A and see what we can see. Okay, so we want A1 or A2 and A2 and B2. So we've got root 3 plus root 2. I'm going to figure out A1 and B1 first, just to see what's going on with this. So that's going to be root 3 squared plus 2 root 3 root 2 plus root 2 squared. So that'll be 3 plus 2 root 6 plus 2, or 5 plus 2 root 6. So A1 is 5, B1 is 2. Okay. Now, what's interesting to note is that they didn't tell me I have to prove that these two formulas both work. Right? They didn't tell me anything like that, so I don't have to worry about that. So if I get an and bn from one method, then like by doing this and raising it to the 2n, I don't have to confirm by doing root 3 minus root 2 to the 2n and show that it is the same a and bn. They're giving me those formulas. Okay, but the thing to note is an plus bn root 6 is root 3 plus root 2 to the 2n, but using my rules of exponents, that's this thing squared raised to the n again. So really it's 5 plus 2 root 6 to the n. And that might be something worth noting. And similarly, an minus bn root 6 is going to be 5 minus 2 root 6 to the n. Okay. So, what are we trying to do? We're trying to do A part, so we just need A2 and B2. This is actually, I mean, anyone should be able to get this one, I would hope. B and C may be a little harder, but A2 plus B2 root 6 should be 5 plus 2 root 6 squared, which should be 25 plus 2 times 5 times 2 is 20. So 20 root 6 plus 2 squared is 4 times 6, 24. So we get 49 plus 20 root 6. Okay. So that tells me A2 is 49, B2 is 20, and we're all set. Right? Yeah. Okay. Now what to do? So, that's fairly quick. I'm trying to weigh my options. Should I sort of putter about, take a look at A3 and B3, A4, B4? Because I feel like I really should get an understanding of these numbers and how to generate them, and talking about ones, digits, and things like that, because I know C is going to be a bit more involved. I could probably do B right now, just sort of messing around. I could probably stumble across on something. I'm just wondering, should I go for B or should I investigate these numbers a bit more? I think in the absence of any clear direction in which to investigate, well, why don't we go for B? Alright, so B was, we want to show that this expression here is between 2an minus 1 and 2an. Okay. So I'll just write that down so I don't have to keep bouncing back and forth. 2an minus 1 is less than that. Root 3 plus root 2 to the 2n less than 2an. So this, it would force this number here to have the exact same units digit as 2an minus 1. That would be what we're forced to have happen. So, should I prove this by induction? That's the question. That's No, I do have the indices, right? Yeah, okay, I do have the indices correct. Well, I know rather naively that this is 5 plus 2 root 6 to the n. I don't think that's going to particularly help me, but how might we show that? Well, if I can borrow some of the stuff I know from Pell's equation, sometimes I think it's fairly good to leave these things together. So, root 3 plus root 2 squared, we know that this is 5 plus 2 root 6. And we know that root 3 minus root 2 squared is 5 minus 2 root 6. So root 3 plus root 2 to the 2n is 5 plus 2 root 6. Yeah, we already wrote this down. I'm just writing it again as sort of some clarity. This should be a minus sign, not a plus sign. And we get 5 minus 2 root 6 to the n. What I'm going to do is I'm going to multiply them together. So root 3 plus root 2 times root 3 minus root 2. This is difference of squares, so this becomes 3 minus 2, which is 1. Now, if I raise both sides to the 2n, I still get 1. What, if anything, does this do to help me? I don't know. Incidentally, so this is because I remember Pell's equation and how those sorts of things work. I keep mentioning Pell's equation. This is not Pell's equations. That's an interesting, a very interesting problem that I'm just already familiar with, having done different math things. It's one that I was familiar with at your age. Whether or not I was quite so good at it, debatable. But so, that's the experience that's informing this raise everything to the 2n and get those two things so that they multiply to be 1. How else might I see this if I were in your shoes and I haven't seen Pell's equation? Well, let's go back a moment for a second. You'll notice that in both B and C, they're talking about root 3 plus root 2 to the 2n. And in excuse me, and in A, to get A2 and B2, we only really need to consider this first equation. So the question has to be asked, why are they even bothering with this one? Why are they even bothering telling me that this is AN and BN, but with the minus sign? Why are we even bothering with this guy? Okay? And I think, it does take a little bit of thinking, but you have to use this at some point. It's additional information that you don't need to do A, but you probably need to do B or C. It's not apparent that you need to use them in B or C, because B or C only talks about the plus. But the minus sign's got to be somewhere, and if we ignore all this 2n stuff, we're left with a root 3 plus a root 2 and a root 3 minus a root 2. And that, to some people certainly, it will cry out difference of squares, product is 1, that sort of a thing. But I think now, knowing this information, then I can say, well, this guy here, he's AN plus BN root 6. This one's AN minus BN root 6. So what if I add these two? What if I add them? If I add them, I'm going to get 2AN on the one side. Okay, so we might even, since we're writing this up, we might clarify things and say 1, 2, we might even have 3 here. These are the things we're going to talk about. We're going to add 1 and 2. So 1 plus 2 tells us that root 3 plus root 2 to the 2n plus root 3 minus root 2 to the 2n is equal to 2an. And at this point, you don't need 3 to see this fact. Okay, I jumped to 3 and started doing Pell's stuff because that's what I already knew. I'd had experience with that, so that sort of to me said, well, you got to do this. But if we just made the observation of equations 1 and 2 and added them together to get the 2an, suddenly you'd start saying, oh, there's a 2an. That's very close to what I want. Now, what we're trying to show is an inequality, and we have here an equality. Okay? So what is there to do? How can we turn this into an inequality? And I think now the thing to focus on is this fella right here, root 3 minus root 2, the extraneous thing. The extra thing, the thing we don't need. Because we want to talk about this. We want to talk about 2an. It's just this that we need to talk about. Now, Oh, I guess maybe we don't need... Yeah, we don't need 3 at all right now. Huh. Okay, well then that's me trying to do Pell's equation and be all fancy. I guess we don't need that. Because what I'm going to say is now root 3 is greater than root 2, and these guys are between 2 and 1. So we'll make this an actual sentence. Notice that these guys are between 2 and 1, so root 3 minus root 2 is less than 1, but still positive. Okay. So this is something that starts off 0 point blah blah blah. Well, if I raise it to the 2n, it's still going to be between 0 and 1. And so this is the real inequality 3 that we need. So let's disavow our Pell's stuff. We don't need this right now. I may come back to it in C part if I need it, but you guys don't need it. You don't need it for B. So what can we do now? So now that I have this, well then, what is there to say? 0 plus root 3 plus root 2 to the 2n is less than root 3 minus root 2 to the 2n plus root 3 plus root 2 to the 2n, which is less than 1 plus root 3 plus root 2 to the 2n. I think there's probably an easier way to phrase this, but this guy here is 2an. And so we'll color code this a little bit. This inequality shows that root 3 plus root 2 to the 2n is less than 2an. And then this inequality here shows me that 2an is less, so subtract the 1 from both sides. So now let's subtract 1 everywhere. So 2an is less than 1 plus root 3 plus root 2 to the 2n. And that tells me 2an minus 1, just subtracting 1 from both sides. So that's what the blue part told me. And then the red part, quite simply, is just, well, 0 plus is just the root 3 plus root 2 to the 2n itself. Combining these two, we get our desired 2an minus 1 less than root 3 plus root 2 to the 2n less than 2an. Alright, so that's B. A little more sentence structure, but they're the inequalities and everything that we need. Okay. Now, I'm fairly certain we're going to have to use this fact in C part. And C part is talking about the ones digits. Okay. So, right off the bat for C, I would say something like, since 2an minus 1 is an integer, because an is an integer, we see that B tells us 2an minus 1 is between these two numbers. So the floor function, this is just the greatest integer less than or equal to, is 2an minus 1. That's the biggest integer that is less than or equal to root 3 plus root 2 to the 2n. What am I going to do with this? Well, this allows me to say the decimal expansion to the left of the decimal point for root 3 plus root 2. The integer part of this guy is the same as 2an minus 1. Okay, so what have I really shown? The ones digit of root 3 plus root 2 to the 2n is also the ones digit of 2an minus 1. And now what does this give me the benefit of? Now I don't need to be dealing with all these root 2s, root 3s, and various exponents. I just sort of need to be able to talk about the 2an minus 1s. That's what I need to talk about. And now I think maybe some of my Pell's equation knowledge might kick in. Because what I'm going to try and do now, because I've seen things like this before, I'm going to try and create formulas for ANs and BNs. Now, I don't think I can get sort of explicit, like you tell me you want n is 7 and I can give you exactly what AN is. But I think I could probably at least get a recursive formula, and that might be something to start with. Because now I've shifted the problem. I'm not talking about root 3 plus root 2 to the 2n. Now my question is just about these 2 ANs. That's all I need to do now. Okay? So, my other observation is this. Root 3 plus root 2 to the 2n. Let's say to the 2n plus 1. He can be split into root 3 plus root 2 to the 2n times root 3 plus root 2 to the 2. Okay, just basic exponent rules. But this guy here is an plus bn root 6. And this one here is an plus 1 plus bn plus 1 root 6. And this here, as I've remarked before, is 5 plus 2 root 6. So let's expand this side out. The 5an plus 5bn root 6 plus 2an root 6 plus 2. The root 6's will come together, so it'll be 12 bn. So together we have 5an plus 12bn plus 5bn plus 2an root 6. So this tells me an, and you can make some comment here if you want to. You can say, like, by comparing integer parts, things like that, whatever you want to do. Basically, it boils down to the fact that root 6 is irrational. If you want to have sort of a lengthy side proof that says, yes, the an plus 1s have to match up with these formulas and things like that, go ahead and do that. But it's largely immaterial. Everyone knows root 6 is irrational, so you don't have to make that giant argument. You really don't. Okay? But if you want to, feel free to try it. And you can even tell me broad strokes what you did in the comments, and I might respond, or someone else might come along and respond and say, that's very good, or you need a little work explaining this. Okay, so there we go. But we get a nice little recursive formula. Whoops, the line went right through. This is what happens when we draw freehand. I should draw the box first and then... Okay, 12bn. Okay. So if this is true, I already have A1 and B1, and I know A2 and B2 thanks to A part. So let's briefly try those out. So I might make a little chart here. N, and we'll, here's our AN, here's our BN. And we're just going to try and fill some of these out, and then how about we also get 2AN minus 1, and more specifically our units digits, so DN. Okay, so 1, 2, this is really the ultimate test here. So we had 5, and we have 2. And what are we saying? Well, we do 5 times the AN plus 12 times the BN. 25 plus 24 is the 49 that we already saw. And then it's 5 times the BN plus 2 times the AN. That's 10, and 10, that's 20. 2 times AN is 48. 98. Minus 1 is 97. So here our DN is 7. Here it's just a plain old 9, so the DN is 9. Okay, so the 3 here. And these numbers are going to get pretty big. Fortunately, we are allowed to have calculators. But what I suspect is this will possibly boil down to, one, I certainly think noticing a pattern. There'll probably be a pattern. I don't know if I'll be able to write enough of the chart to see the pattern. But I also think that this will boil down to an argument of just, well, we really only need the units digit of the AN and the units digit of the BN, and that would simplify my chart. Just do everything mod 10. Because the math still works, we just have to work mod 10. So 3, so that would be 5 times 49, already these numbers are getting kind of big, plus 12 times 20. That's 485. Okay. This 9 just looks weird to me. Okay, and now it's 5 times 20 plus 2 times 49. That's 198. Okay, so 485 times 2 minus 1 is 969. The units digit here is 9. So maybe it just goes 979797. But what I'm thinking is, and I should probably make a note of this if I'm going to change my chart. Since we only need the units digits, we can, and you might want to justify this a little bit more, we can work modulo 10. So just working with units digits, basically. And then it'll all work out. So let's make a different chart. And this one should go a little faster, because I don't have to do as much with my calculator. So I'm going to say mod 10. BN mod 10. And then 2AN minus 1 mod 10. But really that's just equal to BN. So we have 1, 2, 3, 4, and this might be a little faster and get me a better idea of what's going on. I don't know if I'll be able to get up to 8, but so we have 5, 2, we have 9, 0. And then the 5 times 9 plus the 0 doesn't really matter. So 5 times 9 ends in a 5. And then the 5 times 0, again, that doesn't matter, plus the 2 times 9 is 18, so that's an 8. 2 times 5, so every time I see a 5, 2 times 5 minus 1 is 9. Every time I see a 9, 2 times 9 is 18, minus 1 ends in a 7. Look how much easier this is to work out. Alright, 5 times 5, 25, and then 2 times 8 is 16, so 5 and 6, we're going to end with a 1. And so that's a little different, so it's not going to be a 7 over here. And then 5 times 8 is 40, nothing to do there, and 2 times 5 is 0. So 2 times 1 minus 1 is 1. Okay. Now 5 times 1 is 5, plus 2 times 0, it's just going to be 5, or 12 times 0. 12 times 0. So I guess, did I make a mistake there? 5 times 5, 25, and then 12 times 8, 96. Okay, so I got saved there. I made a goof. I was using, it's 5 and 12, and then 2 and 5. So I think I've been saying it wrong. Should I quickly? Well, these ones were all fine, and I did do the 12 with the calculator that time. So it's only 4 that I might have screwed up, but it all worked out. Because 2 times 8 and 12 times 8, of course, have the exact same thing. So the 10 here doesn't really matter. It's the 2. Okay. So I would have been fine either way. 5 here and 2 here, so that's going to be 5. And then 5 here, 2 here, it's going to be 2. Hey! Once we, so it repeats. Because we get 5 and 2 again, so that'll give me 9 and 0. And then 5 and 8. And then 1 and 0. And so it'll go to 7 and then 9 and then 1. And so it repeats. Because it's a recursive relationship, to get the next line, I only need to know exactly what came above it. Okay, so as soon as I have one pair, it's going to repeat. And this, I mean, there were only so many pairs of things mod 10. I can only 100 different pairs. So eventually this would have to repeat. And it happened to repeat fairly quickly. So because it repeats, so every 4 n's, the dn value repeats. Because of our chart, and you could say a little bit more, like it's a 5 and a 2, and we already had that. Or you could say, well, the next line is only determined by the line above it. So we'll say that. So the formula shows the n plus 1 line depends only on the line above. The n line. Okay? So, it repeats quite nicely. And that means our sum is just 9 plus 7 plus 9 plus 1 plus... It's just going to keep going. Now the question is, we're doing 1,867 of these. So 1867 has a remainder of 3 when we divide by 5. By 4. So our sum looks like... we'll flip to the next page, but it's going to look exactly like 9, 7, 9, 1, 9, 7, 9, 1. Just keeps going on like this. 9, 7, 9, 1. And then the last 3 will be 9, 7, 9. So how many of these are there? Well, there's 1867 minus 3 divided by 4, which is, no idea. 1867 minus 3 divided by 4. So there's 466 of these. And then these 3. So this is 466 times 9, 7, 9, 1 plus a 9, 7, and a 9. Okay, so this is 466 times, the 2 9s is 18, the 7 and the 1 is another 8, so that's 26, and this is the same, but it doesn't have the 1 in it, so that's 25, and this is something I can just plug into my calculator now. 466 times 26 is, 12,116 plus the 25 is 12141. And that's our final answer. That I don't feel like that one took me as long as B3 usually does. I thought it was a nice question. Maybe I was quite eager to get into it, and I was because of my knowledge of Pell's equation, so I sort of knew to jump for that recursion formula in C part. You see, I did try and use my knowledge of Pell's equation of a similar problem that I'd seen before in B part, but that actually didn't work out. But it absolutely helped motivate me to get a nice little recursion formula in C part. Overall, I thought it was a nice little question. Maybe a bit too easy for a B3. I don't know. Yeah, sometimes it's hit and miss whether I do these quickly. But that's it. I liked the 2016 senior paper. I look forward to the 2017 paper, both intermediates and seniors. And yeah, so feel free to give a like or subscribe just to show your support. I will see you guys for more math contests in the future. If you're looking for more senior papers, I do have the previous years done, of course, as well. And the next year I will get to will be the 2017. I will see you guys for more math in the future. Until then, take care.